All right, where we left off was the induced EMF due to the change in flux. It is a back current. And there are three things that affect that induced EMF. One is the area. So you could change the area of this thing, and that would change the amount of flux in this thing. So a greater area would mean a greater flux, meaning a greater induced EMF. You could change the magnetic field. By making the magnetic field stronger, you would make more lines of flux in that same area. That would also increase the flux, making an increased EMF. Or you could change the angle of the thing, which basically changes the area of the loop. So either one of these three would change the amount of flux, thereby changing the induced EMF. So once again, we don't have a flux measurer. Normally we measure the magnetic field and we look at the area, and it's the angle between these two. And that's how we determine how much flux there is, and therefore how much induced EMF there is. Okay, here's three examples. So which loop has the greatest EMF at the instance shown above? So a couple things is, we're confining the magnetic field to this rectangle right here, these pink things. And remember, they're dots, not X's, so that means the magnetic field is coming right to your face. Okay, now how they move is like this. So this one in a certain amount of time moves like this, from here to here. This moves from there to there, and that moves from there to there in the same amount of time. So, pop quiz, which one has the greatest induced EMF? Pause and think about it if you need to. And then pause. And so, the one that moves to the right, you've doubled the amount of flux. You've added 4 lines of flux. The one that moves downward loses 2 but gains 2. There's no change in flux. Number 3 over here gains 2 in flux. Well, this one, number 1, has 4 more field lines. 2 has no field lines, and that one has 2 field lines. So of course the one that has the greatest induced EMF is the greatest change in flux per the same amount of time, which is it just gained 4. There's no EMF on this because there's no change in flux. So there's nothing induced on this loop, only this one and this one. But this has twice the change in flux per same time that have twice the induced EMF. Alrighty, so let's talk about this whole induced EMF with the change in area. So you notice we have the rod moving to the right, and with your old right hand rule, if your thumb points in the direction that these stationary charged particles would be in the rod, and the field is outward, so there is a downward force pushing on those charges as this moves to the right. So the length doesn't increase, but the width does. So the area gets larger, not because of the L, but because of the W. So that's what we're going to look at, is how much larger the area gets, and therefore what happens to the flux over there. So the area is your L times your W, but once again, it's not your L changing, it's the W. So we have a certain width, but as we move over to here, we have more width. To find that, it depends on, well, how fast the bar is moving and how much time. So this extra distance or displacement is your velocity times your time, your average velocity times the time to do that amount. Okay? So it looks like it's getting a little more complicated, but it really isn't. This is just the extra distance is all it is. And in real life, you don't care about this flux that didn't change. You only care about the added flux. So you need to know how much added flux there is per that time. That's really all you have to know to find the induced EMF. Okay? So that's what we're doing. Look at the change in flux, which is really the added stuff. And so this is the final flux. We had to add on the distance. The initial, we only had the original width. So we're doing the difference. So blah, blah, blah. It matters how fast you're moving the rod. So the L doesn't change, but how fast. So all we're doing is converting the formula for EMF from flux to time by adding the magnetic field. And since the length doesn't change, we're deriving it down to the velocity. So the moral of the story is the faster that rod moves, the greater the induced EMF. So if this is an airplane wing, left wing and the right wing, flying across the magnetic field in the Antarctic, where the field would be coming upward or away from the Earth, that would mean positive charge would be pushed here and negatives there. And to find the difference in EMF depends on how fast it's going. The strength of the field is not very strong. It's actually pretty weak. But by knowing the length of this, and the longer the wings, the greater the EMF we would have. And of course, the greater the speed. The faster it flies, the greater the difference in potential across those wings. Okay, as an example. So what about the sign of the EMF? So this is the math, okay? It gets you through how to do all the math stuff of what the induced EMF is. But how do you know what direction it is? So Faraday is great for finding the amount, but we're going to go into a new law here shortly that's going to help us in using our right-hand rules to find out what the sign is, or which way it is, which way it moves, which you can figure out by using your first right-hand rule. But there's actually a faster way to do some of this stuff. And it has to do with what's called Lenz's law. So Lenz's law is great to find direction of things. So we're doing the same thing. So as this rod moves to the right, we're increasing our flux. So we have a clockwise induced current this way, lighting our light bulb, because the flux is increasing. And that means it's by your first right-hand rule is pushed downward and it spins like so. Okay? So that current loop generates an induced magnetic field. Because current is moving, that's their second right-hand rule. There's actually one that goes around that. And if you use your right hand and the thumb pointing the direction of the flow of the current at any spot on that wire, let me just do the sideways one going towards the bulb, the field wraps around it. And on the inside of that wire, the field goes opposite of the magnetic field. On the outside, it goes in the same direction. And as it goes downward through the length of that pole, well, on the left side, it opposes the magnetic field. But on the right side, which is in front, the direction it's moving, the rod's moving, it's actually the same field. So just on the bar by itself, if you're looking at this bar right here, because the current's going downward, there's a magnetic field that circulates around that goes down on this side, but comes up on this side. Well, that makes it hard to push that rod. And you can feel it when you generate electricity. It's how a generator works. As you're pushing that bar to the right, as you're shoving that bar over to the right, it takes a force to do that. Because what happens is the direction of the induced EMF makes a magnetic field that's in the same direction as the external magnetic field. That means they oppose each other. That's north fighting north. But here you have a south, because it's the induced field from the current going this way goes in, which is opposite. Well, opposites attract. So in front, the rod's being opposed north on north, but on the back, it's being pulled backwards by the north on south. So it takes physical work to push that bar from the left to the right. You can't get something for nothing. There's no free energy. So you don't just get magically energy and light out of this light bulb for nothing. It takes work of you pushing this bar this way to make that happen. So from right-hand rule 2, that's what we just talked about, and if you followed anywhere with your hand around it, that means the field is on the inside of this at any one direction. It's inward. It's outward on the outside, but it's inward on the inside. And that opposes any change in this bar and this getting an increase in flux. So what happens if you reverse the velocity? Well, remember, if you reverse the velocity, everything's just backwards. That means if you're pushing it back the other way, now the bar is going this way, the field is still outward, now it's shoved upward, the induced EMF is in the backwards direction. And then the magnetic field is just the opposite. That means if the current is now going upward on this rod, now the fields are reversed, and now the North Pole is on the inside, and the South is on the outside, trying to pull it back, so you can't decrease the flux. So it's just the opposite. Oh, there it is. So now if you're going inward, we're adding a smaller flux. Now the current goes in the opposite direction. Okay? Flux is decreasing. Well, that means now you're getting your north on north in front and your north on south on the back of this thing by using that right-hand rule number 2. It opposes a change in motion. So that current loop generates an induced magnetic field that opposes a change. Okay? So now it's out of the page. just like this one. So now you have your north on north here, so it makes it hard to push against that, but you have your south on the back side of this bar. Once again, it takes work to push it that way. The current goes the other direction. So that's how a generator works. You could push the bar one way, current goes one way, you push it back the other way, it goes the other way. In other words, you shake that bar back and forth, you're generating an alternating current, which is basically how our generators work in our power systems all across this earth. Okay? So the induced EMF opposes a change in flux. Well, that's what our Lenz's law is. So Lenz's law is we always have an opposition to a change in flux that causes a back EMF. Okay? So as we're looking at, this is the Faraday thing, but if we're looking for directions, if the flux increases, the new EMF or voltage makes a new field to the opposite, to oppose a change in that field. Okay? So if flux decreases, the new EMF makes a new field to support the old field to keep the change from happening. So it tries to keep it in the same direction. So that's what Lenz's law is. Lenz's law opposes a change in flux. And the induced EMF is in whatever direction it has to be in to oppose a change in flux, to keep the old field the way it was so it doesn't grow or doesn't get smaller. Okay? It's like an inertia. So the EMF does not oppose the B field or flux. What happens is the EMF opposes a change in flux. Okay? So EMF is not affected by a field or the flux. It's affected by the change in. Anytime you have a change in flux, there's going to be a change in the EMF. Okay? So, magnitude of the current. So let's talk about current for a moment here. So if we want to find out what the current is like, well, that's basically your I equals your V over R, or your E over your R. But now since we're looking at the current and not the EMF, the amount of current involved, you just divide by the resistance and there you are. Okay? So it's going to be in the direction of the induced EMF. So in this case, if the direction is clockwise and this bar is going to the right, well, according to Lenz's law, there's going to be an opposition to a change. So rather than getting more flux going north, it wants to oppose it to be less. That means this generates a magnetic field in the loop to oppose the change where that's not a north here. It's actually the opposite. It's a south. Because it doesn't want the field to get stronger. It's trying to keep it small as we increase the amount of flux into there. Okay, so the B field generates a force on the current carrying bar. Okay, so we talked about that a moment ago. So the increase in the B field generates a force on the current carrying bar, so you constantly have to push the thing. Okay, so that's your right-hand rule, the first one. As it goes to the right, there's a force downward on charges. Because you're pushing to the right, what happens is that generates a force pushing the charges down this way. But because you have the current going in this direction, we have an induced force backwards on the bar. So the force on the bar always opposes the external force acting on this to increase the amount of flux. So by the direction of this current going this direction, that makes a magnetic field that pushes backwards onto this thing to oppose you pushing on that bar. Okay, so there are two forces. One is the force on the bar, like you pushing the bar or a cat. Maybe you tie your cat onto that and the cat pulls it across there. Who knows? But there's an external force on the bar, but because of that, there's an induced EMF that creates a backwards force on the bar that opposes a change in flux. So the force on the positive charge is driving the induced current. So the very fact that the bar is going this way pushes the charge this way, but that induced EMF creates a magnetic field that's going to oppose any kind of changes in the flux. Okay. So what if you reverse it? Well, the opposite thing happens. So what they reversed, if you notice, is the magnetic field is now going backwards. Okay, so we're going to talk about what happens as the magnetic field is going backwards as you run out of time in 3, 2, 1.